Just kidding, I've already done 2013. That problem's pretty easy. 2015, I already slept. Okay, let's do 2016 for real. Supposedly I said it was good. Oh wait, no, never mind. This is 2016. Okay, I already did 2016. 2017, P3. Okay. Let me SS this. How is this so... Okay, there. Okay. Let's have a look here. So... a uniform mass... Okay, whatever. I don't care about the numbers. It's all just the same pretty much. Okay, so I'll call this H. Okay. Share that as 30. Okay, no friction. Okay. So the total kinetic energy, that's pretty simple. Conservation of energy. So the only relevant thing to keep in mind is probably that let's call that L. The total gravitational potential energy at the start is just mg h plus L sine theta. And then it's just asking for total kinetic energy. So since energy is conserved, it's the whole thing. Okay. Okay, now it's asking for the angular velocity of the cylinder around its axis the moment it reaches the floor. Oh, wait. Also, I just realized that this is actually wrong. You don't need the L sine theta because I didn't read it properly. It's just going to be mgh. Or sorry, mgl sine theta. You don't need the h because it's only asking for the table. So you can just set that as the reference point. Okay, so the moment it reaches the floor. So now you're going to use mgh plus L sine theta is going to be equal to 1/2 mv squared 1/2 I omega squared. Then yeah, you're probably literally just going to substitute v is equal to omega r, and then you have that mg h plus L sine theta is Heivium is equal to fm r squared w squared plus 1/4 r squared mr squared w squared, I mean omega squared, and then I think you can just combine here and then divide everything by m, so you get the gh plus L sine theta 4 3 r squared square root is equal to omega. I don't know what that number is, but that is, I'm pretty sure what it is. Rotational kinetic energy is just going to be 1/2, because if you look at the relationship here, you see that, or sorry, wait, what is it asking for? Rotational, wait, rotational, to total kinetic energy. That's my bad. It's going to be 1/3. Just because you know that the total kinetic energy is going to be 3/4 mv squared, and this is 1/4 mv squared, so it's a pretty trivial conversion. Yeah, okay. Then, okay, so it's asking for the horizontal speed d. That's no problem. Okay, so yeah, okay. For this, I assume you just solve for the linear velocity here, and then you just do vxt. So let's just go ahead and do that. So the linear velocity, you have the mgl sine theta is equal to 3/4 mv squared. So you have that v is equal to square root 4/3 gl sine theta. Okay. Okay. Yeah. So you have this, and then yeah, so you know at that point that all the velocity is just in the x direction. So then you can now just directly, oh, hi Terry. You can now just directly solve for time. So you have that t is equal, or sorry, that h is equal to 1/2 gt squared. You know that the acceleration of the thing is just g. So then you have that t is just equal to 2h over g square root, and then the horizontal distance d is equal to vt is equal to, you just multiply these two together, which I can't do this math in my head. Whatever, like the g's cancel out and it becomes like 8hl sine theta over 3. There you go. Okay. So that is part D. Part E is asking, okay, so is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the total kinetic energy of the cylinder? So this is obviously equal to, because the total kinetic energy is just going to be the gravitational potential energy, which is not dependent on inertia at all. Okay, so then rotational kinetic energy is going to be less than, because rotational kinetic energy is I omega squared, and Yeah, because I is less, it's going to be less. And then is the horizontal distance. I'd imagine it's just greater than, like, probably, because trying to think now. Is it going to be greater than? Yeah, it's going to be greater than, for sure. Because if the inertia is less, then it'll probably travel further. That's just my thinking. Yeah. Okay. So, I mean, I might as well check my answers. I'd find it hard to believe any of those are wrong, but okay, yeah, whatever. Check this. Equal, less, greater. Easy. Okay. That's what I put, right? Equal, less, greater. Brilliant. Okay. Okay. 2018 problem 3. Let's do it. Okay. This problem. Okay. Yeah, I skimmed over this when I was looking for them, and then this one actually looked really sick. So, okay. I'll probably do this in 2 screenshots. Ha. Okay. So, let's paste this in really quick. Okay. So I'll just do this down here. Okay. So I'm pretty sure that the equation for just do inertia is equal to something like mr squared. And then I'm pretty sure that m is equal to like lambda. That's not how you draw lambda. Lambda something? Lambda dx or no, dm is equal that or something. So maybe you like integrate to get m. I guess that sort of makes sense or so. Okay, well, let's just try that. So this is inertia. dm is equal to lambda dm. Yeah, okay, that makes sense. So, and then r here. Oh, okay, so you need to do like parallel axis theorem. So I think what we're just gonna do is we're just gonna solve for like the normal, and then we can just parallel axis it at the end. So you do from minus r to r of mr squared lambda dx or so, and then now you just integrate, I'm pretty sure. So it'll become the integral minus r to r 2m. So L squared we can substitute for 2r. So it's like 4r squared times mr squared dx. That's probably not good. Why is everything canceling? Huh. uh, okay, that's not... Oh, wait, there's also an X. What? What the fuck do I... Oh, I see. Okay, so I put an X there, and then this cancels, and then it's like m squared over... Oh, yeah, it worked. M squared over 2x dx. Okay, so it becomes m squared x squared. I think one of the m's should have canceled. Wait, oops. I don't think that inertia is mr squared. I think it's just r squared. Hold on. Inertia of a rigid body integral. Okay, yeah, it's just r squared dm. That's what I thought. Okay. Yeah, that makes a lot more sense. So this goes away. This goes away. This goes away. So this comes mx squared over 4. And then from minus r to r. So it becomes m wait. I'm literally trolling. Okay, no, you do. Okay, so minus mr squared over 4 equals 0, and then you do parallel axis theorem. So you do 0 plus m. Yeah, okay. Then plus ml squared over 2 equals ml squared over 2. That's part A. It took me way longer than it should have, but yeah, there we go. Okay. A thin hoop. Okay, sure. I total of the hoop rod system about the center of the hoop. Okay, that's like pretty free. I think you just like add them. Wait, am I trolling? Do you not just add them? Oh, also, I realized there's a much easier way to do this integral. You can just evaluate it from 0 to L, and then it just comes ml squared over 2. Okay, whatever. Ignore. Okay. So, hoop rod system. Okay, yeah. So this is just going to be ml squared plus 3ml squared over 2. So it's just going to be 5ml squared over 2. Okay, a constant force is exerted. Determine an expression for the final angular speed W. Okay. So it's constant force. So you have that. So there's probably like 2 ways to do that. Well, I don't know if there's 2 ways, but the way that I think of doing this is literally just T net is equal to I alpha is equal, that's a terrible alpha, by the way, is equal to like RF. Yeah. So then alpha equals RF over I. And then W is then just equal to the integral of this dt RF over I delta t. And then you just substitute in I is 5ml squared, and then F is F. Okay, that's part C. Oh, whoa, we're on a slope now. Good shit. Okay. Yeah. So I don't know if I already screenshotted that, but if I did, then whatever. Should probably also whatever. No way, that's wrong. Okay. On the figure of the hoop rod system below, draw and label the forces that act on the system. Okay. So, okay, first of all, we know it's rolling without slipping. So there is a friction force. There is applied at the point of contact. Then there is mg straight down. And then there is Fn straight up. I mean, not straight up. It's in line with it's perpendicular to the slope. Justify your choice of direction? Mg always points straight down. Friction, like, just goes in the opposite direction of motion, and then Fn goes perpendicular to the thing. I don't know what. Derive an expression for the change in height? Oh, I see. Until you're just, okay, yeah, So, express your answer in terms of ML. Wait, what is L? Oh, yeah, I see. Okay, yeah, So, this is literally just conservation of energy. Nothing deep here. MGH is equal to rolling without slipping. Okay, well there is a linear velocity and an angular velocity here. So 1/2 mv squared plus 1/2 iw squared. And I honestly can't believe I'm actually solving this, but I guess I'll do it. So we can't use v, so you just do v is equal to omega r. And then so 1/2 oh, okay, wow. Wait. Oh, R and L are equal. All these R's I've been using are just L. I'm stupid. Okay. Yeah, so this is just L. This is L. That's pretty funny, actually. I don't know how I didn't notice that. So yeah. L squared omega squared plus 1/2 1/4. I might as well just simplify that. ML squared W squared. So it's just 3/4. So 3/4 L squared W squared is equal to GH. So then H is simply just going to be equal to 3L squared over 4G. Right. Oh. Oh, and also, this is a slight misnomer. I just realized we can actually just use I. And also that the inertia I calculated was wrong. So, one moment. Ignore all of this. So then, plus that. So H is just equal to 2mg on the bottom 1/2. Oh, oops. Yeah. Okay, is there another problem? Another part of this? Nope. Okay, let's check our answers. Yeah, okay, so they just did it from 0 to L, which is what I was thinking. Like, after I did it. Okay, this is what we got. That's what I got. Easy. FN. Yeah. Oh. Friction was wrong. I put friction. Which way is the ball rolling? Oh, the ball is rolling counterclockwise, which means that friction provides a positive torque. Okay, I missed that. That's pretty smart. I didn't think about that. Oh. Sure. Yeah, that's fine. Yeah. Yeah. Oh, yeah, it was free. It's exactly what we did. Yeah. Okay, that's easy. Do like one more or two more. Okay. 2019 S1 P3 and S2 P3. All right, I'm gonna go fast. Hopefully. I guess I'll just do more in later. Oh, what the fuck? Torch. Okay. That is a scary looking diagram. No worries though. Oh my god. This question is long as fuck. My god. Okay. I'll probably just end it here then, after I finish this. That's pretty ridiculous. Okay. I wonder if there's like copyright for doing FRQs like in public, you know? That'd be something. Okay. Let's have a look here. A horizontal circular platform with rotational inertia I sub p rotates freely without friction on a vertical axis. A small motor-driven wheel that is used to rotate the platform is mounted under the platform and touches it. The wheel has radius r and touches the platform a distance. Okay, whatever. That's fine. Oh, I see. Okay. So d is just like a torque constant or torque radius. Angular speed w sub p after t. Okay, sure. WP of the platform. Okay, so this is pretty easy, I think. So you have that the t net is equal to I alpha is equal to d, wow, df, that's not an f, d, there we go. Okay, df, that's still not a very good f, but I guess we'll take those. So then you just have that alpha is equal to df. I don't know what the fuck is going on with my mouse right now. df over I, and then I mean it's constant force, so you don't actually have to integrate. You can just use the kinematics equations, but it's whatever. I'll just integrate, so you get that W is equal to df over I times t. I mean delta t, whatever, doesn't matter. Of the kinetic energy of the platform. So this is really easy. Yeah. So we know that there's no linear, or like the center of mass of the platform does not move. So the only kinetic energy is rotational. So you just have that k equals IW squared. And then I'm like too lazy to compute that, but I mean, you just square this and multiply it by I. Okay. Derive an expression for the angular speed omega w when the platform has reached angular speed omega p. Okay. So, what is r? Oh, I see. Okay. So you know that this wheel and this platform have the same linear speed at this point. So, it's just like calculating a gear ratio in a car, I'm pretty sure. So you just have that like omega w r is equal to, oh, we can just use, that's really funny. Okay, omega p d, right? That is the linear velocity there, and that's so ww just equals wp d over r. Easy. Okay. A student holds a disc directly above. Okay, it's just conservation of momentum. Wow, this problem is actually really good for our test. Okay. So IP. Okay, this disc has the same rotational inertia as 2IP WF 2. That's not the right thing. Oh my god, what the fuck? On the graph of the previous page, draw a line of best fit. Okay, you just draw it. I'm not. Okay. So calculate the rotational inertia of the unknown object. Wait, what? Oh, I see. So I guess I will do this then. Well, I'm not gonna actually calculate the slope, but Loaded? Okay. So, we're not going to graph it, but I will explain or show how the graph would be relevant to solving this problem. So, assuming that we did have a line of best fit, we would have the ratio WF over WI. I mean over WP, well, whatever. It's okay. I don't know what is the graph actually? What are the axes? Okay, so it is WI. Good. Yeah. So we have this ratio. We know that. Oh, we have that IPWI is equal to IP plus IU WF. So then IPWI over WF minus IP, which is just IP times WI over WF minus 1 is going to be equal to IU. And then you can notice that this is actually right here, just 1 over the slope. And then there you go. And I'm pretty sure that they'll give you IP. I don't remember actually reading the question. Yeah, so they tell you what IP is, and then you can just plug that into your calculator, and then you're done. Okay. Which of the following expressions is true? Justify your answer. Okay, so like the surefire way of doing this is to like literally just plug in numbers and like empirically test it. But I don't know. I mean, we can probably think about this algebraically. So would KF equal KI? Find that unlikely somehow. Unless the collision is elastic. Oh wait, no, the collision is inelastic, so we know, of course, that this has to be true. I'm stupid. Right. I'm pretty sure that you can, yeah, like you can just think about this as an inelastic collision. I'm pretty sure. So the kinetic energy has to be lower because it sticks. I'm pretty sure that line of reasoning makes sense. Hold on. The center of mass is not directly aligned with the axis of the platform. Whoa. Huh. I think that means that IU is going to be greater. Now, my math justification for this is very non-existent. But the way I'm thinking about this is that like in a hoop, the rotational inertia is greater than a solid disk because there's more mass farther away from the thing. And if the center of mass is shifted one way, that means that there's more mass farther away from the thing. So it's greater than? I think. Sort of makes sense. Maybe, possibly. I think this is also just like an... Oh, wait, actually, no, I do have a math justification for that. This is just parallel axis theorem. It's going to be greater than. Because, just by parallel axis. So, let's go ahead and see. I did. It's correct. Yep. Nice. Nice. Yeah, sure. That's exactly what I did. Brilliant. Cool. Nice. Nice. I got that. Okay. Oh, let's go. Let's go. And I got parallel axis. Okay. That's really cool. That's really good. Okay, so yeah, yeah. I think. Well, let me see how long the last 2019 FRQ is. If it's like super long, then I'm not gonna do it. But or actually, I might do it still. Part F, but minimum height. So this is okay. So this is just set Fn to 0 and then do circular motion with like the centripetal force equation. Then, or I mean, centripetal whatever, centripetal acceleration rather. You do v squared over r, and then you know that Fn is 0. That's like probably how you do this, and then sphere is released at rest from some point A without losing contact with the track. Okay, I actually want to sort of do the first two parts of this. I don't care about this. Okay, this is like very free, whatever, who cares? Wait, actually, calculate r, the radius of the loop. Oh yeah, so you do v squared over r. Okay, yeah, sure, fine. That's pretty free. Okay, I'm gonna do part A and part B at least. Actually, I might just like do the whole thing. Why not? Okay, this will be our first screenshot. So let's have a look here. Okay. So let's have a look here. So inertia. Okay. So look here. Okay. Okay. So let's have a look here. Derive an expression for the minimum speed of the sphere center. Okay. Just allow it to pass point A. Okay, so what you can do here is if it's asking minimum speed, that means just as it's about to lose contact. So we can assume that Fn is 0. So therefore, the only force that acts on it here is just mg. So you have mg is equal to mv squared over r. So then this cancels, and then v is equal to square rg. I want to actually check my solution for that before I continue, because I imagine everything will go very wrong if I mess that up. If I did that wrong, I don't know how else you'd do it, probably. But oh, let's go. Okay, nice. Let's go. Okay, I'm very happy about that. Okay, so b is equal to rg. Sure. Okay, so now you know. Okay, well, I mean, like, I don't even. Okay, so it says rolling object, and it rolls without slipping. Okay, so then you have that mgh is equal to 1/2 mgr, might as well just simplify v squared into that, plus 1/2 b m r squared, like lowercase r, that is. And then what do we just have for h? Okay, so we can just cancel all this nonsense. And then we have that h is equal to g big R plus b small r squared over g. So we can simplify this further. It's just r plus br squared over g. Pretty sure that should be right. Check that. Okay. What is 5? Oh, okay, they just simple whatever. I don't care. Um, 1/2 plus. Wait, what? Oh, right. I'm stupid. Plus, of course, the gravitational potential energy here, which is g times 2r. Okay, whatever. That's fine. Probably would have noticed that when I'm checking. Okay. So I don't care. Plot the release height h as a function of b. Okay, so you just do that, and then like literally, I think you just plug it into conservation of energy, and then you just use v is equal to omega r, and that's like the whole thing. Also, sorry, this should have a w squared there. Okay, this like algebra is bad, but whatever. Yeah. So you just plug it into conservation of energy. That's like the bottom line. You just plug it into conservation of energy. Yeah. Like, do I even care? Calculator. Yeah, this is probably just conservation of energy again. Like, I don't care. That's whatever. In part B, the radius r of the rolling sphere. Oh, that's why there's no angular speed. I see. Okay. Yeah. That's pretty interesting, actually. That's pretty funny. The value minimum release height h. Huh, so that's actually pretty interesting. R squared. That's a great question. Well, what was our equation for h? Okay, I need to actually write out my equation properly then. mgh. Oh, well, I guess that, like, that doesn't even matter. Yeah. Like, r squared w, like, I guess that doesn't even matter. Well, I mean, I guess it'd be greater than. I'd guess it'd be greater than. Just kind of doing mental algebra in my head. I imagine it'd be greater than. So it's like we can actually find out. So that's whatever. Less. Oh, it's less than. Interesting. Oh, yeah, I guess that makes sense. Huh. Okay, well, whatever. I didn't really do the second FRQ very like properly. I just kind of did everything fast in my head, so I'm not actually that concerned about that. Nice. Ha. I normally do play MKDS, in case you're wondering. I'm actually quite good at the game, but yeah, I didn't play. Didn't play right now. If you look at my, hold on. I also don't know when you sent that chat message, so you like realistically probably not even listening to me, but all my MKDS replays are there. And they're all quite good. Most of them are like top 30, top 20-ish. So yeah. Yeah, so anyway, that's it for this. I'll probably upload this to YouTube. Hi, Terry. Were you watching that whole time? Oh, you follow the category. Nice. Well, I'm about to end, probably. By the way, for other MKDS streamers, this guy, MKDS Able, he streams fairly regularly. And unlike me, he actually has good stream quality. And he's very good. So I would recommend him. There's another guy, Utter Randomness, who's also very good. And he doesn't stream very regularly. He streams fairly irregularly, but when he does stream, it's good. I'm not turning my cam on, Terry. And I'm trying to think of other people who stream MKDS. Like basically no one. Well, puddings sometimes, but they're like extremely infrequent to the point where I wouldn't even count that. So yeah. I would if you want to watch other people who stream MKDS, Able and Utter Randomness are good. Oh shit. Well, I'm in high school right now and I'm realizing that dream, so you can probably do it too. Are you on the players page by any chance? Don't know what I'm talking about, then this. There's an update. That's me right there. 17th worldwide. Doing a little bit of... Thanks, Terry. Yeah, dude, you wish you were 5th in the US. That's like top 50. Actually, that's a great question. Before I end stream, I'm going to check that. Not UK, US. Where is top 50 US? I mean, top 5. Nick Welch. Oh, he's like way better than top 50. Let's find out where he is. 31st. Not bad. Not bad. You do wish you played this game, bro. Oh my god. Anyway, I'm gonna stop streaming and do my CS homework now.